Welcome to our session on adapting conventional software testing techniques for modern artificial intelligence solutions. This is part 29 of our AI Audit Exam Prep series. Today we will explore how established testing methods like A/B testing, unit testing, integration testing, and others can be repurposed to validate complex algorithmic models. Before we dive into the details, let us discuss why this matters in your daily professional life. As an auditor or technology leader, you will frequently review systems developed by external vendors or internal engineering teams. Understanding these testing frameworks allows you to critically evaluate whether a proposed technology is truly safe, reliable, and financially viable for your corporate workflows before any contracts are signed or systems go live. Let us begin with the concept of A/B testing. At its core, A/B testing is simply a competition between two different versions of a system to determine which one delivers a better outcome. In the context of intelligent systems, data plays a highly unique and significant role. To find the best performing model, an organization might change specific features within the training dataset to see how that single alteration impacts the final results. Testers can also evaluate entirely different mathematical architectures and algorithms against each other. They might also adjust the hyperparameters of the system. Let us clarify what hyperparameters are. Think of hyperparameters as the master dials or settings configured before the machine even begins its learning process. Imagine you are making coffee. The water and coffee grounds are your basic data, but the water temperature and the brewing time are the hyperparameters. By creating version A with one brewing time and version B with another, you can scientifically determine which produces the best cup. Our next topics are unit testing and integration testing, which are closely related but serve distinct purposes. Let us tackle unit testing first. Modern technological solutions rarely rely on a single, massive program. Instead, they leverage multiple individual components and models working together to perform a larger function. Unit testing is the practice of breaking down this massive system and testing each tiny component individually. For instance, consider a smart warehouse robot. It uses one model to recognize boxes, another to calculate weight, and a third to navigate around shelves. Unit testing involves isolating just the box recognition model and proving it works perfectly on its own before testing anything else. Once you know the individual pieces function correctly, you move on to integration testing. Integration testing evaluates how these multiple components interact with one another when combined. This is crucial because a small error in one component can create a massive cumulative impact on the overall behavior of the system. Think of it like a plumbing pipeline in a house. The pipes, the water heater, and the shower head might all work perfectly on their own during unit testing. However, if the connector between the heater and the shower head leaks, the whole system fails. Testing the data flow and the entire pipeline as an integrated unit ensures that codependent components are fully harmonized. If the initial data filtering process fails to remove toxic inputs, the downstream decision engine might act maliciously or provide terrible outputs. Moving forward, we must examine objective verification. A technical solution is useless if it does not solve the actual business problem. Objective verification revisits the business goals and success criteria established very early in the use case development stage. We do this by measuring key performance indicators during the prototype phase. These indicators might include prediction, accuracy, inference time, and the cost to serve per 1,000 predictions. Let us pause and translate inference time. Inference time simply means the amount of milliseconds or seconds it takes for the machine to process a new piece of information and spit out an answer. Why is this verification step so important? Imagine you build an automated customer service agent that gives perfectly accurate answers, meaning the technology functions properly. But if it takes 5 minutes to answer a simple question or costs $50 per query, it has utterly failed its business and financial goals. Before any program can go live, an oversight body like an AI steering committee will demand formal proof that these overarching objectives have been achieved. Let us shift our focus to code reviews. Even the most advanced autonomous systems are built on a foundation of traditional software code. Human engineers write readable scripts to clean datasets, train the models, and build the application programming interfaces that let humans and machines communicate. Code reviews involve using automated scanners or human analysts to read these readable instructions and hunt for errors. This works wonderfully for simple, deterministic models. Deterministic simply means that the system is highly predictable. If you push button A, you will always get result B. Because the rules are rigid, humans can easily read and understand the underlying algorithm. However, traditional code reviews are nearly useless for the core decision-making logic of large, complex, non-deterministic models. Non-deterministic means the system might provide different, evolving answers based on its own internal learning. You cannot review the code because the machine's knowledge is not stored as readable English instructions. Instead, the encoding is represented as very high-dimensional matrices of numbers. To put that in plain English, imagine trying to understand the plot of a movie by looking at an Excel spreadsheet containing 1 billion raw color codes for every pixel on the screen. Humans simply cannot digest or interpret that level of raw mathematical data, making manual code review of the core intelligence impossible. This leads us directly into our final technique, which is black box testing. When the source code is completely hidden from you, or when the matrices are too complex to read, black box testing is used to deduce how the system operates. You treat the program like a sealed, opaque box. The technique involves systematically applying different stimuli and checking to see how the system responds. You must rigorously keep certain variables constant to isolate and analyze subtle behavioral changes. Think of trying to figure out how a strange vending machine in a foreign country works when you cannot read the buttons. You put in a coin, push the top button, and get water. You put in the same coin, push the bottom button, and get juice. By systematically varying the inputs during both training and inference, you can map out the hidden decision paths of the machine. While black box testing is incredibly useful, and sometimes the only testing method available, it is exceptionally time-consuming and demands massive resources to map every possible scenario. Let us briefly recap the major concepts we have covered. A/B testing allows us to pit different datasets and algorithms against each other to find the ultimate winner. Unit testing ensures individual pieces work perfectly, while integration testing confirms that the entire data pipeline flows together without cascading errors. Objective verification proves that our technical achievements actually meet the core business and financial requirements. Code reviews are excellent for the surrounding infrastructure and deterministic programs, but fail against the unreadable matrices of complex models. Finally, black box testing allows us to safely map out opaque systems by systematically changing inputs and studying the outputs. All the important topics and concepts from this session are covered in the multiple choice questions on RooCloud.com. You should ideally solve the chapter-wise questions to reinforce your learning before moving to the next session. Thank you for joining me, and I will see you in the next session.